Empire acoustical systems are designed and engineered to offer a variety of abatement solutions to specific airport, military, industrial, and highway situations. In association with a number of colleges, universities, governmental agencies, and private testing facilities, Empire Acoustical Systems has become the leading pioneer in the design, construction, and testing of economical, efficient abatement structures. As the result of a sizable grant from the State of Ohio Department of Development, Empire Acoustical Systems, in conjunction with the nearby North Central Technical College, maintains a large test facility at the Mansfield, Ohio Lahm Airport. Extremely sophisticated sound source and recording equipment permits testing over a wide range of frequencies. The structure was designed to facilitate changing or reconfiguring panels with different reflective or absorptive characteristics. Tunnel effects can also be created. Special panel units such as the Vista View panels, doorway and gate panels can be evaluated for situations having special or unusual requirements. A slightly different type of testing was conducted recently. Empire Acoustical Systems developed a thrust director to meet United States Air Force requirements for jet engine exhaust deflection on parking ramps and other engine run-up areas at Grissom Air Force Base. The design criteria applies specifically to the KC135 air refueling type aircraft, which have been retrofitted with significantly more powerful engines. Although deflection barriers are not new, design and performance data was inadequate for an application to these particular engines. Consequently, the authorities at Grissom Air Force Base arranged to have a 140-foot section of the Empire-developed thrust director undergo on-site testing with one of the re-engined Stratotankers. John Ramsey, research engineer at the NASA Lewis Research Center, directed the field testing. Dr. Gerald Gregoric, associate director of the Aeronautical and Astronautical Research Laboratory at Ohio State University, was responsible for all data analysis. Although the primary purpose of the Air Force barrier is to protect personnel, vehicles, and other aircraft on the ramp from the jet blast, there are significant noise abatement advantages also. Typical sound transmission class for this barrier would be 25 or greater. All components of the Empire thrust director were fabricated and roll-formed in accordance with the exact engineering design criteria developed by Empire Acoustical Systems. The steel, the galvanizing, and all other materials, such as fasteners, were certified by the suppliers to be in conformance with Air Force specifications. Strain gauges were installed on the various components of the structure's support member. The wired components were then used to replace existing support members. The function of the strain gauges was to measure the stress on each component of the support members. Stress was measured in a lateral and longitudinal direction on each truss. This was a most important test. Although engine data was provided by the manufacturer, the structural strain on the structural supports was a relative unknown within precise limits. Therefore, the Empire thrust director was supported on 3- and 4-foot centers. The test results showed that 4-foot centers were more than adequate, and this could result in a significant cost savings on the overall thrust director installation. 4-inch colored rope tufts were secured to the thrust director surface facing the starboard engines. The tufts were attached in a 1 square foot pattern that spanned a 44-foot section. Of particular interest was tuft movement in the jet exhaust overlap area that occurs when both engines are running at high throttle settings. Static pressure port manifolds, each containing 10 static pressure ports, were installed on the thrust director. The manifolds were aligned with the center line of an outboard engine and the center line of an inboard engine. The third manifold was installed midway between the outboard and inboard engine center lines. Each static pressure port was connected by plastic tubing to a manifold which allowed monitoring of the pressure at individual ports or on the total surface at each location. Almost a mile of plastic tubing was used to connect the static pressure ports to the recording instruments. Pitot tube supports were installed at the bottom and the top of the thrust director surface in alignment with the center line of an outboard and inboard engine. Each support carried 2 pitot tubes. one at 12 inches above the surface and the other at 24 inches above the surface. All tubes were connected to a manifold for total or selective pressure readings. Plastic tubing from the static ports and the pitot tubes were connected to a specially designed manifold. The manifold allowed selective reading of static pressures and total pressures at various points on the Empire thrust director. Surface temperature data was acquired by using a variety of probe and bolt-on type thermocouples. Air temperature thermocouples were mounted through the surface at various intervals. These monitored air temperature data at specific heights above the thrust director surface. Air temperature was also recorded at ground level. Accelerometers were installed at two heights on the back of the thrust director in line with an outboard engine. The frequency and amplitude of all vibrations were recorded at the two positions during the entire test sequence. It was cold, windy, and snowing lightly as all instrumentation was given a final calibration. All data links and pressure tubes were secured with sandbags. The KC135 Stratotanker was maneuvered into position at a precise distance from the Empire thrust director as required by Air Force specifications. Alignment of the engines relative to the instrumentation placement on the barrier was extremely critical. Once positioned, the aircraft wheels were chocked as part of the normal safety precaution observed during the test. Temperature and wind velocity data to be factored into the test results was provided by the Air Force Weather Station on base. Again, as part of the safety precaution observed, a full flight crew was aboard the aircraft during the test. Communication to the aircraft commander were established via radio and intercom. Actual testing began with a smooth, gradual run-up of all four engines from ground idle to 80% of takeoff-rated thrust. In the second phase, all engines were run up in increments of 20% to allow measurements at each throttle setting. In the next sequence, the inboard engines were incrementally increased from idle to full power. As the final test, the same procedure was followed with the outboard engines. Prior to the initial four-engine run-up, smoke generators were placed behind the thrust director in the structural supports. With the engines at ground idle, the smoke generators were ignited. As the smoke billowed out, the throttles were advanced gradually until 80% of takeoff thrust was reached. The purpose of this test was to determine if all the jet exhaust was deflected upward with no horizontal component being blown straight back. As you can see, the smoke remains in back of the thrust director, clearly indicating that all of the jet exhaust is being directed upward as designed. Pressure readings from the static ports and the pitot tubes were taken from the manometer as a cross-check and redundant system for the other pressure data recording equipment. The main data acquisition and recording was a van with its own regulated power supply. A vibration analyzer maintained a steady flow of information from the accelerometers. Temperature readings from the air and surface thermocouples was recorded on a thermocouple data log. Strain gauge readings were recorded manually. Pressures from the static ports and the pitot tubes were sent to a pressure transducer and automatically recorded. A second van with an onboard computer was used as a redundant data recording center. It was used also to provide additional temperature information and analysis. A third van unit was used to record on videotape the smoke test and the tuft movement patterns. Further surface temperature information was generated by the use of heat tapes. The dots darkened in sequential order as the temperature increased on the face of the thrust director. The patterns of tuft movement was recorded for the entire duration of the test. This visual record reflects the variations in jet exhaust flow at the various power settings and the effect of inboard, outboard, and both engine configurations. Final analysis of this and all other test data was done by Dr. Gerald Grigoric, Associate Director of the Aeronautical and Astronautical Research Laboratory at Ohio State University.